In section 2.6b, we're going to be focusing on absolute value transformations and a follow-up from our off-campus learning day. And today we're going to focus on flipping and shifting our absolute value graph that is done diagonally and horizontally and vertically and upside down. So first we want to start off with just the basic premise of understanding the lines y equals x and y equals negative x. So I'm going to start off by saying, hey, let's understand that the slope of y equals x is 1 and the y-intercept of y equals x is 0. So I'm going to graph that, start at 0, and I'm just going to go up 1 over 1. And we're going to obviously see that this graph of y equals x is a 45-degree angle going up, slope of 1, pretty normal and pretty straightforward here. Now, as we compare that to y equals negative x, that has a slope of negative 1, but still has a y-intercept of 0. So as we draw that second line, we see our slope is a negative 1, going up 1 over 1 and up to the left. And that line, when we draw it, obviously is going down from left to right. And so we just kind of understand the fact that these two functions, the outputs have been flipped. And what I mean by that is any output on the blue line that is negative has been flipped up to the positive here. So this magenta point goes up to that point. This green point down here is going to come up to this point. And so it's really a flip over the x-axis when we take and multiply the output by a negative. So since we're kind of comparing these, we're going to say, hey, the first one has a slope of 1, the second has a slope of negative 1. But the negative slope, how does it change the graph? All right, I think the simplest thing we can say is that it is going to flip all the outputs from positive to negative or from negative to positive. Because in the same way, on the opposite side, you could have this point flipping down to that point. All right, now let's take a look and let's sketch the graph of y equals the absolute value of x. So the equation for the y equals the absolute value of x, as you know, is in the shape of a v. And so here's our v, and the shape of y equals absolute value of x is going to come up like that, and then our v is going to come a 45-degree angle from the other direction. So there's the y equals the absolute value of x. And we're going to say this is done in purple. Now, we're going to take and comparison this to the equation of the negative, the opposite absolute value of x. So we have the opposite of the absolute value of 0, which is 0. We have the opposite of the absolute value of 1, which is negative 1. So 1, negative 1. Opposite absolute value of negative 1, which is the opposite of 1, which is negative 1 again. And very quickly you begin to see that this graph is going to be flipped of the purple graph over the x-axis. And so it's symmetrical over the x-axis, and the magenta graph is a flip over the purple graph when we change the outputs. So all of these points are reflected down to the other graph. So we've plotted those points. We kind of got a feel for it. And so as we conclude about the graph of the opposite of the absolute value of x compared to the absolute value of x, I hope at this point you can very quickly see that when you multiply the outside or the output of a graph, it's going to flip over the x-axis. The new shape, instead of being a valley, is going to be a mountain. An upside down V instead of a valley. All right, so now let's kind of look at what this impact does, and let's kind of play around with some movement on our graphs. On each of our problems, we're going to characterize them by the following. We're going to characterize them by, are they a mountain or a valley? We're going to characterize them by the slope of each number. We're going to characterize them by the fact, does it go right or left a certain number? We're going to characterize them by saying, does it go up or down by a certain number? And so we really are just going to have to try to consider all of those possibilities in our problems. So let's look at our first one. The negative means it's going to be a valley. Sorry, a mountain. Upside down is a mountain. The slope of this first one is 1. That means up 1 over 1. Because it's x minus 2, it's going to go right 2. And because it's a plus 3 on the outside, it's going to go up 3. So let's take and go right 2, up 3, and put a point. Our slope is 1, 1, and it's a mountain, so we're going to go down on a slope of 1, 1, straight down there from the vertex, and then straight down here on the other side from the vertex. Had the slope been something different, we would have angled it more. We're going to see more of those later in the chapter. Let's look at example 2. Once again, we've got an upside down absolute value because of that negative sign. The plus 3 in the middle causes it to go to the left 3, and the minus 1 causes it to go down 1. So let's go left 3, down 1 with the slope of 1, and remembering the fact that it is a graph that is a mountain and not a valley. Moving down. Here we've been given some equations. Let's put some arrows on here because remember there's more off the graph than on the graph. And we're going to have to kind of assess what it is. So our first assessment is the fact that it's a mountain. The second assessment is that the slope of this mountain is 1, 1. So the slope is 1. Now we have to look, where is the vertex? We have shifted to the right 3, and we have not shifted up or down. So I'm going to say the vertical shift equals 0. So let's fill this in. Y equals, it's upside down, so it's negative. The slope is 1, so I don't need to put a number here. It's shifted to the right 3, so that's x minus 3. And I guess we could say it's plus 0 and with a 1 in front here. So those numbers that are in magenta and or highlighted are really not necessary, but they illustrate that we have some factors that we've considered, but they're no impact on the problem. Let's look at number 4. Once again, putting my arrows on there. Once again, it's a mountain. That means it's a negative. The slope of our mountain is 1. It's shifted left 2 and up 4. So left 2 and up 4. So let's write our equation. Y equals negative 1, absolute value. Left 2 is x minus 2. Up 4 is a plus 4. The only piece of information in this one that's insignificant is that negative 1. We need the negative, but not the 1 as we're looking at these. All right, let's move on. Finally, we're asked to write an equation for the translation described below. I think the best way to approach these problems is really very quickly just to sketch them. So I'm going to sketch this with a vertex at 1, 2, 3, 4. It's negative, so it's going to go down. So that's our basic problem that we have. And the translation is saying, hey, where do we translate from this line, y equals negative x, over to this positive? Well, remember, it's still going to be a negative, but it's moved to the right 4. What does that imply? Right 4 is x minus 4 with no vertical shift, so plus 0. Once again, that plus 0 is not required, but it just helps us to understand that we've considered that the fact that it doesn't move up or down. Let's graph this one. Over 2, down 3. It's a positive absolute value, so this is going to be going up as a positive. So let's take a look here. Once again, we've shifted right 2 and down 3. So y equals the absolute value of x minus 2 minus 3. There is a plus out front, which does denote the fact that it is a valley, but it's not necessary to put that plus. All right, as we look at our homework tonight, we've got a couple different situations where we've got 12 through 18, and on these first, we're just going to be graphing or writing the equation on each one of these. It's just we have different illustrations, equations to graphs, graphs to equations, once again, equations to graph, and then stating the value of the shifts of x's and y's, and just trying to say, hey, what is the equation for all of these problems with many different presentations. I hope this has been helpful understanding flipping and shifting absolute values diagonally and the key ideas that are involved there.